Okay, so I'm going to talk to you about my current passion this evening, which is a project I've been working on since around 2007. So, you know, in business and entrepreneurship, everybody likes to talk about a 4-year cycle whereby if you can't get your product to the market and start making money on it within 4 years, then it's not a viable business. Almost every business I've been involved in, the time cycle has been much, much longer than that. And here we're talking about 18 years from conception to utilization. And so I'm going to talk about Earthfence, which is our name for a proprietary software-defined deep space radar system that we innovated and deployed at the Algonquin Radio Observatory.
The lights wash out the screen.
Oh. Does somebody have control of the lights? And I should say, as we go along, I'm happy to take questions. If you want to ask something, just then ask me a question. As Mike suggested, I was a professor for 20 years, so I'm used to people interrupting me by now. Great. So you probably recognize the logo, maybe from the building up on the highway. That's another Thoth facility where we have a 2,000 square foot clean room where we manufacture space equipment. We have an administrative block. A restaurant, which if anybody wants to lease, come and see me. And then various other units in the back, which actually may be leased quite shortly. And then we're also putting in a remote mission operations center. And there's a high bay to store some various large pieces of equipment. But today I'm mostly going to focus on what's going on at the observatory. So this is a real picture. It's taken by another local named Wesley, whose handle is Cowboy, with a camera. And there are these astrophotographers who stay up in the middle of winter at night in their sleeping bags until it's minus, 10, and they cool off all their cameras, and then they stay up all night just to get that perfect picture. And it is very nice. So this is not false color. This is the Aurora Borealis over the observatory. So not everybody knows that in 1959, the federal government executed a massive build plan to build the largest antenna in North America at the time in the middle of Algonquin Park. So why Algonquin Park? First of all, there's a radio silence. There are no buildings for 50 kilometers really in any direction. It's very cold in winter, so that gives you good viewing conditions in the RF up to high frequency. And it also has readily accessible bedrock. So this antenna weighs about 3,500 tons. A 2,000-ton concrete building with walls 1 meter thick, rebar reinforced walls, supports a 1,000-ton moving mass. All of the infrastructure on the top here down to there will rotate more than 360 degrees on the roof of the building. So this project came about as a collaboration between the UK and Canada. The original contractors were Freeman Fox Associates of London. And they designed the antenna. They also designed the Parkes antenna. This is almost an identical copy of the Parkes antenna, except the Parkes antenna has a slightly larger skin because they don't have to deal with snow and wind in winter, as we do. And then over a period of about 3 to 4 years, an intensive construction campaign was undertaken to build the antenna. The team were only given one thing, a 1.5 megawatt feed off the national grid. And that's it. They had to provide absolutely everything else for the estimated 1,500 workers who were involved in this. So some of you are probably of an age to remember when the construction was occurring, and almost not a month goes by without somebody coming to tell me about their experience of whatever it was, laying the tarmac, building the buildings, or whatever it was. This is one of the high points constructing this facility of many, many people's careers. And I don't just mean the scientists, I mean all of the workmen and the laborers, as well as the scientists and the engineers. And so it is really quite an incredible piece of machinery. Because it was built in the 60s, they built it to last. This thing is extremely heavily engineered, and a testament to the fact that it's fully operational today indicates to you, this kind of infrastructure was enduring in a way that maybe modern structures aren't going to survive 70 years in operation. The antenna was constructed, and then very early on it started to make some scientific discoveries. It discovered various interstellar chemicals for the first time. And around 1965, it discovered or invented a very long baseline interferometry, which is a precursor technology to GPS. And so in this technology, if you take two antennas and you look at the same object on the edge of the universe, you can determine whether one antenna is closer to that object than the other antenna, ultimately to a millimeter. And in 1965, this antenna paired with the antenna at the Herzberg Institute in Penticton were both pointed at a quasi-stellar object, and they made this measurement, and it allowed them, through the rotation of the Earth and the summing of data, to determine the distance between the two antennas, measured at 3,000 kilometers to a precision of around 30 meters. And so this was the first demonstration of these precision technologies. So not many people realize that everything on Earth, in order to precision map its location, we do it using pulsars, which are at the edge of the universe. So it seems a little strange, but that's how our ultimate grid reference accuracy is obtained. And so there is a program called the International VLBI Service growing up out of this technology, where a 10-nation conglomerate point about 20 antennas at the same pulsar for 2 minutes in a 48-hour observation session once a week, and then they rally and point at another pulsar, and then they rally and point at another pulsar, and through a series like triangulation or multilateralation, they relate the coordinate parameters on Earth. And the reason is that we need these remote sources is that everything on Earth is in dynamic motion. The crust is rebounding from the ice, from various other effects. The daily surface of the Earth goes up and down 10 to 15 centimeters a day in a force driven by the moon. Very similar to the tides, but the rock is more elastic, and so the deflection is smaller. So there are all of these measurable effects going on, as well as plate tectonics, and other things that move around. So in order to relate things on Earth, we have to use an external reference. And we've discovered and invented this method using pulsars out of astronomy that allows us to do this. And so physics is reciprocal. Using this technique, we can learn about where we are. We can also learn about the objects. And so a very long baseline interferometry survives at the observatory today, and we are delighted to be partnered with the Theoretical Institute for Astrophysics at the University of Toronto in a program where we regularly run VLBI sessions with students as training, and also to develop research outcomes with the other large antennas around the world. So it's more or less reasonable to say that in modern astronomy, nearly all of modern astronomy is based on using interferometry. So the advantage of interferometry is if I build a massive dish, I can collect lots of photons coming from an object, and I can get a great signal to noise. And I can also resolve how big that object is, and my ability to resolve angle goes to like the distance, the diameter of the antenna. So the bigger the antenna, the smaller distance I can resolve. If I only have a small antenna, I can't do so well at the angular resolution. Now in interferometry, if I take two antennas and I phase them up so that I match the light phases together and put them together, I can build a theoretical aperture, which now the resolving power goes like the distance between the antennas. So I can take two smaller antennas and place them 4,000 kilometers apart and end up with an aperture which is 4,000 kilometers across. This is underpinned by mathematics from Lord Rayleigh, who first defined it. And it works exactly the same for optical as it does for RF. So, and indeed, if you're thinking, if you're puzzling about the radio nature of the antenna, if you just think about it as being optical, you won't be very far wrong. The photons behave almost exactly the same way. So what we're doing here is we're looking at objects which are almost at infinity. And so we could imagine a point object which is almost at infinity, emitting radiation, and maybe it's emitting radiation isotropically, so just a large, we can imagine a large spherical ball of radiation passing out into space. By the time that wavefront intersects the Earth, the curvature is almost non-existent because the distance from the object is huge, and so it's almost flat or planar. And nature's shape for focusing planar radiation onto a point is a parabola. And so that is why these antennas are parabolic. So the construction of the antenna, the design goal was not to have any one of the metal plates out of position more than 2 millimeters from the true parabola. And the antenna was constructed and then measured, this is in 1965, to get every single plate to within a millimeter using steel tapes loaded with 100-pound weights. We didn't have interferometry, we didn't have lasers, so we used steel tapes. And you had to keep the steel tapes tight, because otherwise you get an error over the size of this antenna, so we put 100-pound steel weights on it. So real testimony of phenomenal what people can do with even relatively simple tools to construct very complicated things. I first saw this antenna in about 2006, 2005, and I saw it at night. I arrived late. I was invited by one of my colleagues at York University to see it, and it was covered in retroreflectors, so it looked kind of bright and very pretty at night. And then we came back in the morning, and it was extremely rusty. It was quite clear that it was not being maintained up to the standard that one should. And I looked at it and I thought to myself, you know, somebody should do something about this. And I had no idea it was going to be me. So fast forward to around 2007, the Harper government was in power, and budget cuts were on the horizon. Every department was required to cut their budget by 10%. Now, this is the federal government, so this is not a discussion, it's an order. And so each department drew up a list of things that it might keep, it might get rid of in order to save the money. Algonquin was on the list. In the week that the ADM had to make the decision, the antenna broke. And so rather than worrying about anything else, simply crossed the line out of the budget. So at that point, my company, which is quite a small technology company, ThothX's Inc., we stepped forward and we said to the federal government that we would like to take over the antenna as a turnkey operation. It's full of bespoke pieces of metal and gears and spares and things like that, that if you removed, it would be very difficult to carry on running the operation. And we would like to take it over, and we would provide it for the government use. And after about 16 months of legal wrangling, finally the government agreed, and we took over the antenna in January 2008. The electricity was down, it was -10, and we arrived and there were doors missing off the building. My first job was to look for bears. So it took quite a long time to do the restoration. Before you can worry about science and high technology, you have to have heating and shelter and food and things like that. So if you've been to the observatory, you'll know that of the original about 50 buildings, the site was much more extensive when it was originally built. There was a 2-kilometer interferometer array with 33-meter antennas and a shed 1.5 kilometers long. And various other pieces of infrastructure. In the 90s, the government reduced the size of the facility and demolished about half the infrastructure, leaving about 12 buildings and about 50,000 square feet of space on 150 acres. and removed some of the other sites. So there was still quite a fair amount of work to be done. On site there's a 25-bedroom lodge that had to be refurbished. All of the heating systems were broken in every single room. All of the water systems were smashed. The building had hard frozen. And so that was quite a big job to do the reno. And so in the early days, the antenna didn't work. It had a major failure of one of the main gearboxes. So in the early days, we actually had guests to the observatory who would come from a kind of outward bound technological experience and stay for a couple of days, and that actually funded the startup phase of the business. And so then we worked on refurbishing the buildings and getting the heating systems and the water systems back online. And then we started working on the antenna. And so it turned out that one of the 250-ton gearboxes that supports the 1,000-ton moving mass had collapsed and required refurbishing. So no instructions, no drawings until about a year into the project. So in order to fix that gearbox, we had to cut off the deck using plasma cutters, remove the 1.5-ton lid off the top of the gearbox, crane the gears out, each one the size of a small car, and stack them in custom cradles on the deck. And then we had to cut out, using angle grinders, the 100-kilogram bearings because they were too badly damaged to be able to get them out. And then we had to remove the lock nut this big off the end of the shaft in order to get the final bearings off the end of the shaft. And that took 1,000 repetitions, 1,000 placements of a 100-ton pneumatic jack to turn it. The torque required was equivalent to hanging 10 of my full-size trucks on the end of a 1-meter ruler. After we did that, then we had to jack it back again and jack the lock nut back onto the end of the shaft. And we knew we got it down because all the bolts would shear off. So if you've ever done these things, don't stand behind the bolt. When a bolt shears, the head flies off backwards. And so we knew this was going to happen because we'd done it enough to know. But you hear this ping, 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 ping noise, and that's the heads of the bolts flying off and hitting the wall on the other side. So that was a long process, and I had quite a lot of different people come and help me. We filmed a chunk of it on Discovery Channel, which Mike is asking for the videos for the library, and I'll see if I can dig those out. So we were followed by Discovery Channel, and they shot about 4 or 5 episodes on the refurbishment of the antenna and the development of the VLBI there. So as we did this, if we back up to the beginning of Thoth Technology, in 2001, we formed a technology company which was basically to spin out the technology developments of my university research. For the first project that the company did, we did a feasibility study for the department, DRDC, the Defense Research Agency, to see whether you could turn Algonquin into a deep space radar. Again, had no idea it was going to be me at the time. So we hired one of my colleagues who did the math for us and laid out the equations. And it turned out that we could basically expect to see objects in geostationary orbit, which is 50,000 kilometers from Earth, using a radar system that leveraged the advantage of a huge antenna. Again, we didn't know that it was going to be us when the study, we didn't even have the antenna at the time we were doing the study to find out. When the antenna became available, we were interested in it for planetary communications initially, but we also recognized, having done this study, that there was potentially a unique opportunity here to take something which was already existent, that might cost you $1 billion to build another one, and then repurpose it into another use which would have a very, very profound modern purpose. After we'd finished refurbishing the antenna and making it work, then we moved on to designing the radar system. We did that in collaboration with a number of other companies, but essentially it's an all-Canadian. It was designed entirely by Canadians. The software was all developed by Canadians, and it's all proprietary to Thoth. So we called the system Earthfence, and the idea is to secure the locations of all of the spacecraft in space. We're all aware of this idea that if there are many collisions or a few collisions in space, that could snowball into an effect where small fragments could fly off and start to damage the primary orbits that we use to provide services. We've become very, very dependent on space. Your banking will stop. Your internet will stop if the geostationary spacecraft goes down. There are multiple layers to this dependency. There's a low Earth orbit layer where the likes of Elon Musk are deploying mega constellations of 10,000 spacecraft to provide you low latency, direct communications. A little higher than that, there are remote sensing satellites that fly about 600 kilometers above the Earth, and they want to be relatively close because they can see the ground better. It's just like a pair of binoculars. If you're closest to the object, it's going to be bigger. They fly around 500 or 600 kilometers looking at the ground, and they have resolutions now on the order of 10 centimeters. You can almost tell who it is. You can see how many people are standing in the queue, and you can begin to tell who it is from the kinds of resolutions and the adaptive optics in the unclassified domain. And then you probably have to bet that in the classified domain there's probably even better technology available than that. And so these things are very, very useful to us. We use them for mineral surveys. We use them for all sorts of purposes. Above that, there's a kind of a middle orbital zone around 3,000 kilometers up where the GPS satellites live, up to 20,000 kilometers. And they are rotating in a special pattern and providing timing signals for us so that our GPS antennas can pick up multiple timing signals and triangulate where we are. And then above that, at 36,000 kilometers above the ground, there is a very special orbit called geostationary. And in geostationary orbit, a thin ribbon of spacecraft exists that turns around the Earth exactly the same speed that the Earth rotates. And so they appear to be totally stationary in the sky. And that has the advantage that I can take an antenna and bolt it to your house and then begin to immediately receive or transmit signals to that spacecraft, and I never have to adjust the antenna again. And so that is the basis of satellite TV and various other services. And the orbit is particularly significant for the military because it has a constant stare on the ground. Small low Earth orbit spacecraft, they come and go over the horizon in about 20 minutes. You can see them at night disappearing. They're coming and going. So that's not so good because your adversaries could know when that spacecraft's gone, and then they could do something before the next one comes back. And so with geostationary, you don't have that ability because you can constantly look at the ground. And so geostationary has become absolutely critical for the defense of the realm. And in fact, the US General Chance is on record as saying if World War III breaks out, it's going to break out in geostationary orbit first. For if I whack your spacecraft in geostationary orbit before you get mine, then you cannot send the drones, you cannot send the pilots because you don't have command and control anymore. And so this is a very, very contested space. And as well as the various civil services that are deployed, there's rumored to be all manner of different kinds of anti-satellite systems deployed in this space as a contingency should things get nasty. And so these spacecraft, it's very difficult to deploy to 36,000 kilometers above the Earth. It requires the biggest rockets that we build, like the Ariane 5s. Each rocket launch is a couple of $100 million. The spacecraft on the rocket, $300 million. And then there's an orbital time, so we're talking about each asset is worth $1 billion. Or this is where the Lamborghinis of the space world are parked, as I like to say. And these spacecraft are surprisingly close together. They can be separated by only a few kilometers. It's an active space, so there are a public catalog of objects in geostationary orbit, about 1,100 active objects. And then there is a classified catalog that we're not allowed to look at, but we can know the magnitude of it. It's about a third of the public objects. So it's about another third of objects. And those consist of secret spacecraft we don't want to tell anybody about, secret spacecraft of other peoples that we don't want them to know that we know about, and things of that nature, things that the military would rather keep quiet. So these spacecraft, their safety of flight is currently coordinated by the United States Space Force, and they, through a civilian service, broadcast the positions of expected ephemeris for each one of the objects in space and a 3-hour timely update. But Space Force doesn't want to do that anymore. That's a civilian service that they feel that should go somewhere else. So one of the innovations and the changes in my market is that this is going civilian now. The military want to do military things, and they don't want to support the civilian activities anymore. And so last year, the Department of Congress mandated the Department of Commerce to take over space traffic management. So that is a service that monitors these spacecraft, and it's in everybody's interest they don't hit each other. And there are obviously degrees of sophistication of the operators as to how well they understand where their spacecraft is and how well they have it in control. And different operators have different sophistication. And so there's also a requirement for an independent monitoring system. So most operators have a means to try and drive their position locally, but the governments need to understand where all these spacecraft are as well to try and mediate and avoid collisions. And indeed, it may be surprising, maybe not because we have the nuclear industry, but Canada carries the liability for these spacecraft. That is, if a spacecraft injures someone, it is not the operator who's responsible, or if it causes damage. It's not the operator, it's not Telesat who run our geostationary, it's the government of Canada. And so that's enshrined in the Outer Space Act, and if the government wishes to make it the operator's problem, then they have to pass laws in the local country in order to make it their responsibility. But ultimately, internationally, it is Canada that carries the can for anything that was launched in the name of Canada. And so clearly, the Department of Defense has a vested interest in monitoring these assets because it has a sovereign requirement, it's inherited a sovereign requirement over monitoring them. So our technology is basically a software-defined radar. We use supercomputers to do all of the analysis. Everything's digital. We leverage the massive size of the antenna in order to illuminate objects 50,000 kilometers away. And then we time the time it takes for the radiation to go out to the object, bounce off it, and then come back again. And then we divide by the speed of light times 2. And it's times 2 because it goes there and back. And that gives you very precisely a range to the spacecraft. And through the various timing technologies that we deploy, we can measure the position of these objects at 50 million meters to 3 meter accuracy. And a lot of this work comes out of things that were developed in astronomy and then applied through radar. And so we now operate a fully live space situational awareness service to Canadian government clients with our partners MDA Space, Canada's biggest space company, under a 5-year standing service agreement with the federal government where we monitor the positions of spacecraft of interest to Canada and then supply them with those locations in under 2 minutes latency. So this is essentially a live update space traffic management. And so with the accuracy, with the 10-meter sub-accuracy and this continuous monitoring, then the government can be proactive about any issues that are happening. So the operators typically file flight plans as to what they're intending to do, so we know what's going to happen. And any deviations from those plans, now that's a cause for concern and interest. The plan now is that Space Force is going to train the world as to how to do civilian space traffic management, and the task will revolve around with the sun, from North America to Europe to Pacific, and then back to North America to provide a continuous 365 days, 24/7 service to monitor the position of these spacecraft and to generate things called NOTAMs, which are basically service notifications to the operators that they have a problem and they need to do something about it. And so one of the, so we developed this service here and deployed and calibrated it. We did a whole series of technology demonstrations for the federal government through DRDC and directly with the military to proven out the service. And this year, well, we're just about starting full service negotiation. It's fair to say that the contractual negotiation took about as long as the technical solution. And so, yeah, when I'm talking to foreign governments, I say to them, you know, now imagine a procurement system that's like your military, and now imagine one that's slower. And then we're getting close to what's going on in Canada. So, you know, if we have a problem in Canada, it is one of the government procurement, the speed of government procurement is really holding down industry, and I'm sure it's not just mine that they're holding down. The 20 months to negotiate a contract is normal. So, and it doesn't have to be that way. So, we have the service operational, but the problem is these spacecraft rotate around the Earth at the same speed as the Earth rotates. So we can only see a third of them. And it became very quickly apparent that in order to be able to offer a complete service, then we needed to see all of them. So sophisticated clients understand, so if Space Force asks me to look at something, they already check to see I can see it. Less sophisticated clients might just give me a list of stuff that they're interested in, and then it's my job to see which ones I can see when and where. But if I can only see a third of the object, and you ask me to look at a particular spacecraft, they all have numbers, a NORAD ID. So we're into 60,000 at the moment. We're very shortly going to break the 70,000th catalogued object in orbit. And so an unsophisticated client might just fire IDs at me and ask me whether I can see them. And if the answer's no, 66% of the time, then very soon they'll stop asking me. And so it became very apparent in our business that we needed to go on a global expansion plan. And so we launched what I call my megalomaniacal global expansion. And so my current endeavor is to deploy the same technology in Australia, Portugal, and the United Kingdom as rapidly as possible using 32-meter antennas that we've acquired in these other countries. So I'll talk a little bit about that. And this will provide us 95% coverage. And so 95 is the yardstick. So that is 19 times after 20, I can see your spacecraft. One of the nice things about this business is that I kind of feel that it's AI proof. The AI, even if you get the AI to do all the analysis technique, they still need the data. The AI can't just make up where the spacecraft are. And so maybe the analysis block is quite vulnerable because you could advance the software analysis continuously through application of more and more smart AI. But ultimately, even the AI has to be fed the raw data in order to make the inference from the data. And so the sensor providers are safe in this new environment where you can generate things on the fly in AI that would take you hours and hours. You can do it in minutes now. This is slides crept in from my recent BT presentation. There are a bunch of these antennas around the world. So in the 70s, in order to offer international telecommunications, the world built 30-meter class antennas for the Intel SAT Early Bird series. And these allowed countries to place 250 simultaneous international telephone calls using these giant wooden desks where operators would plug the things in, like you've seen in the old movies. In fact, we have various of those desks around the place. And so this was the only way to make an international telephone call. About 160 of the antennas were built around the world in order to support this global infrastructure. The frequencies that we use now have moved on. We've moved up in frequencies because we're able to design more carefully the antennas, and we can get more data packed down at higher frequencies. So these antennas have lost utility, but they just happen to be perfect for doing deep space radar. Part of our quest is to find companies like BT who have 3 of these on one of their sites and persuade them into a new business model where they can refurb their existing facility and then start offering independent radar positions to their government. So whatever we think of our friend to the south, he is incredibly good for my business. It's like a seismic change. 2 years ago, it was about what we could do to augment the US capability. And the idea that we needed to duplicate any capability that the US had was an anathema, even to our military. Now no one thinks that. Now everyone thinks that the only way forwards is to have an independent capability, and if you're not independently able to observe something, and you're entirely dependent on somebody else telling you what it is, then you're very vulnerable, because they might not tell you, or they might tell you something else that just turns out not to be true. And so this is really being felt across the world, particularly in Europe. The Europeans are quite frankly appalled about what's happening at the moment, and that is totally shifting the paradigm of the defense industry to a footing where each nation bloc, the EU, requires its own independent capability so that it can independently verify. And so that has been extremely powerful for us. Although countries are prepared to buy data from each other, they would much prefer to have a sovereign capability now. A lot of it has been caused by the various retreat from the international obligations that the US had, and the various other things that are going on that we won't get into here. But it has seriously changed the way the world thinks about defense. In Canada, we have a massive growth opportunity. We've determined that we're going to increase our defense budget by 1% of GDP. So that's $180 billion. So there is no problem with funding for these kinds of activities. And one of my mantras is to spend as much of the world's defense budget as possible without killing anyone. And information services are the way forwards. If I can show you informationally that they're not coming to get you, then the world is a safer place. The more information we have about it, the better it is. And so that's one of the raison d'etres of our business is knowledge. And also, if I have knowledge, and an independent knowledge, it kind of puts people off from trying to do something because they know I'm going to find out. So I alluded to what's going on in space. This is Elon. Elon has 6,000 spacecraft in orbit, more than most countries. He's intending to deploy 10,000 in the full constellation. China plans 10,000 mega constellations. Japan plans a mega constellation. The world is building these giant constellations. Telesat plans to deploy 300 spacecraft. OneWeb, another operational space service, plans. And the services that we're being offered are extraordinary. Really, I had no idea that I would have direct-to-satellite communications from my truck. I just installed Starlink Mini on my truck, and in the middle of Algonquin Park now, I have much higher safety because if my truck breaks down, I can make a phone call, whereas previously I would have been out of cell range. And so these, are very important technologies that are really changing the way that we do business and also enhancing people's personal safety. But it is causing a congestion issue when you look at graphs that show that kind of exponential rise. So why do we choose radar? So oddly, the US military use optical antennas to do this currently because it's quite hard to do the radar problem. They have a couple of stations that do radar, but there's one in Boston, and then there's another one in the Marshall Islands that do radar, but they're very, very expensive to operate in the US military. They cost $1 billion a year apiece in operating costs. So they use a lot of optical sensing technology to do this, but obviously optical has some limitations. The primary one is that it's cloudy, or it's snowing, or it's sunny. Those are the ones that would stop you from doing it. So if this is going to be a real-time monitoring system, it really can't be that if it's cloudy one day that you don't have the data. Okay, that's not an operational traffic system. On Earth, every real-time system uses landing or navigation system uses radar. This is how we land the planes. This is how we have automatic stopping cars and so on. And I would argue this is why Elon has not achieved level 4 autonomy in Teslas yet, because he has an ideological mandate that because we can drive cars through our eyes, not very well, then he can navigate them using cameras. And although Waymo, Mercedes all have level 4 autonomy, Tesla, you would think, who have been at it longer than anybody else and spent more money on it than anybody else, do not. And that is because Elon has refused to use LiDAR or radar technologies to navigate his vehicles, and so they have trouble, for instance, telling white-sided trucks from other things, and that's been causing accidents. So the beauty of radar is it works all the time. It works if it's snowing, it works if it's sunny. The only thing that really stops is if it gets really windy and we need to stow the antenna. But those events are fairly rare. It offers this very long-range detection. It offers this very high accuracy. It also offers a different data set from optical. So if I take an optical picture, I can say very precisely in the plane of the sky where the object is, but I have absolutely no idea how far away it is. It could be a large object a long way away, or it could be a small object quite close. And indeed, with the geostationary spacecraft, these objects are not more than 1 pixel in the camera. They're that small. The equivalent measurement of a radar looking at geostationary is to be able to see an insect at 50 kilometers range. And so those are the kinds of things. So we're ground-based. We're not vulnerable to collision with space assets. In LEO constellations, one of the concerns about LEO constellations is if an adversary comes along and whacks one of my LEO spacecraft, I might not know. I might think that it was just an accident that happened to this spacecraft. And they could create a hole in my visibility, and then they could do something while I'm trying to clear it up and close the visibility gap again. And so that makes that scenario quite vulnerable. And there are other things that could cause vulnerabilities, such as cosmic, solar events, where the sun emits large amounts of coronal mass periodically and can completely interrupt radio communications and other forms of communications. And so we're also less vulnerable to physical attack and sabotage. And again, if I go and destroy somebody's low Earth orbit spacecraft, I might have a great deal of deniability over it. And so one of the very important things here is blame attribution. The governments really want to know who did it, because that makes a really big difference. Like, was it an accident, or did somebody come and do it to us deliberately? And if they did it deliberately, who was it? And so, by contrast, attacking an asset on the sovereign nation's ground is entirely different kinds of kettle of fish by comparison to the kind of deniability that you could get if there was a collision in low Earth orbit. The system we developed, we spent about 25 years of programmers' time writing the software suites and testing them and making it operational. We were a long time in calibration. We were about a year to get the accuracy down to the 10-meter level. And eventually, it turned out one of the programmers had transposed the 5th digit of the speed of light. And so he just transposed 2 of the digits when he'd written it out. And so that was causing a kilometer difference in the solution. So, you know, sometimes these small things cause problems, and you learn lessons as to how to avoid these things, like don't hard code speed of light. So our system is it's software based. We basically, a Windows 10 industrial computer generates a series of custom radio pulses which go to a spectrum transceiver. The spectrum transceiver builds the pulses and then it transmits them through an amplifier chain out of the antenna. They come out of the middle of the antenna, they hit a subreflector here, which illuminates the main surface, and then they travel 50,000 kilometers into space. Some of the photons bounce off the spacecraft, and then some of them come back to us. Not many. 1 in 1 quadrillion come back, so that's 1 with 15 zeros. So every quadrillion photons we fire out, we get 1 back. But through the magic of a technique called pulse compression radar, we can make this work. We can get the signal to noise. So I tell people really just to suspend belief over these things. But there is a mathematical technique that we can use called pulse compression. If we know what the outgoing pulse is, we can combine it and we can hunt through the original receiving data and see whether there's a match. And that's a process called convolution. It's a mathematical process where we combine the original pulse, actually the complex conjugate of it, with the recording. And then if there's a match, there will be a sharp spike where that waveform happens to match in the data. And that can be used to amplify the chirp that you would hear back from the return by a factor of about 10 million. And this is one of the reasons that we can get the gain that we need to see geostationary. So if we use a 46-meter antenna like this, as opposed to just a monopole whip antenna, the gain is 65 million. And the way to think about it is, instead of the radiation going off in all directions, it's highly concentrated into a small patch of sky. And the bigger the antenna, the smaller the patch of sky. And so that's where the gain amplification comes. Because we're using a monostatic radar, that means that we use the same element to receive and transmit. We get the gain of the 65 million on both sides, both in transmit and receive. And then applying pulse compression, we get another gain of around 10 million. And when we stack all of these factors together, it's enough for us to be able to see these objects 50,000 kilometers away. So the other advantage is that we are very, very precise in the position. So there are no calibration parameters. You don't have to tune it. The only thing that you do is divide by the speed of light. So Einstein was right. You don't even need to worry about the speed of light in a vacuum. It doesn't matter. We did the calculations on that. And so that provides you with a very precise measurement. And there's no free parameters that people can adjust and get wrong. And then we also are able to discriminate objects very close together. So in optical, you can't really see objects like less than a kilometer apart. They kind of blur into one. With this system, you can see two objects at 60 meters apart at 50 millimeters. And so clearly that's very important for the new various space activities. Right now in vogue, in geostationary orbit, we launch a mission extension vehicle, and it goes into space, and it docks on the back of a 20-year-old spacecraft that we happen to find very useful. And it takes over, it grabs onto the back of it with grappling hooks, and it takes over the flight dynamics. And so the spacecraft can run out of fuel, and then we're still using the communications bay to be able to communicate with the ground. And so we can renew and extend the life of these spacecraft. So that's becoming very popular, and obviously requires some quite careful orbital precision so that you don't hit each other when you're trying to do the docking maneuver. Maybe. Oops. Go back one. Sorry, I'm hopping around in this. That's where I want to be. Oh, the picture wiped the data. It sounds all quite complicated and so on. At the bottom end of it is a tiny bit of metadata that comes out of the end. Okay, so this is like less than a kilobyte. And each one of these records represents an observation made by the radar. So the radar fires a series of pulses, maybe 4 or 5 pulses, and then it coadds them to get a bit more signal to noise. And then if it sees an object, it basically thresholds the result. And so anything that peaks above the threshold, it says, that's a potential space object. And then we download every 3 hours the 50,000 object catalog. And then a Bayesian inference AI filter compares every single object that we see to every single object in the catalog every time and sees whether there's a match. If there's a match, then it declares it's likely on orbit ID. Sophisticated analysts won't take any notice of that. They'll do their own analysis, but other people might want to know what it is that they think that we're looking at. And then we basically timestamp it to a millisecond. And then we give the angles that the antenna was pointed at and the range to 10 centimeter precision on the object. And then we also give the RCS of it, and we identify this as real data so that you don't confuse sim data with real data, which is a big problem. And so this is basically the record. So we collect about a megabyte every time we fire the radar. It goes to a supercomputer cluster, which is distilled in about 20 seconds into this metadata. And then that is the data that's supplied to the global repository. So around the world, the militaries and the civilian navigation systems are building these giant data lakes where they suck in all of this data. And then analysts, teams, other contractors can come take the data out, turn it into product, and provide it to the mission analysis teams in order to make decisions about how to analyze and whether to warn operators. So our strategic partner in this business is our MDA Space. So it's fair to say that MDA is like Canada's leading space company. They're based in Brampton. They've just built a new building there in Ottawa, and the primary people that I deal with are in British Columbia. And they have built a geointelligence business based on their synthetic aperture radar expertise. So they've deployed a constellation of radar sats, starting with radar sat 1, radar sat 2, and then radar sat constellation that provide exquisite radar imagery. So it can see through clouds. It can measure things like earthquake deformation, and it can provide quite accurate mapping. It can provide information about crop management and droughts and things like that. And so they were very interested in adding the space domain business to their business. And then we also partnered with an American company called Comspoc. So Comspoc was run by another entrepreneur, Paul Graziani. He developed a software package which he gave away to students, and that was the key. And so he basically trained entire generations of university students for decades on how to use his software package. And his software package became the premier software package for doing the orbital dynamic analysis. And then he recently sold that company to a large, to ANSYS for $678 million. And so, but he retained the Comspoc part of this business. So this is a unit which is dedicated to using data from us and from other kinds of sensors. So they take all of these different kinds of measurements and then they turn them into orbital ephemerises and they generate conjunction alerts and so on. So basically you can get everything that the US military do in a single box from these guys, but it's got better graphics than they do. They've been partnered with us for a long time. They provide calibration analysis for us, and we provide the radar capability. And so, you know, all great innovations come about by some kind of rivalry. And the reason that we developed the radar system is because Paul Graziani, his arch nemesis, worked for another corporation, a state lab called Lincoln Labs. And the head of Lincoln Labs would say to Paul, well, you can never take over space traffic management because you can never build a commercial deep space radar system. And so you can never take it over from the military, and it's always going to have to be something which is done by governments. And so Paul was desperate to prove him wrong. And so he discovered that we were building a deep space radar, and he was so determined to prove him wrong that he funded us $1.5 million to develop a deep space radar. So he could go to a conference, which I wrote a paper for, but it was US classified, so I couldn't go. I couldn't see my paper. And he presented a paper at the classified forum at Lincoln Labs to prove the guy wrong. That's one of the reasons why the radar came into existence. So it's sometimes like, you know, it's like those little personal rivalries turn into these kinds of things. We all like to think that business decisions are made by accountants in grey offices and so on. But I think some of the disclosures more recently about how things come to being when Elon writes to one of his friends and says, will you invest in this? And he's like, will $2 billion do? That's not diligence. That's who you know, not what you know. So a lot of these kinds of business interactions, I think, comes down to quite a personal interaction with people. So they've been very important to us, and MDA have provided us lots of expertise, particularly on synthetic aperture radar, which I think I can show in a minute. Okay, I'm going the wrong way, that way. So this is the control room at Algonquin. The software, we developed about 8 software suites. So on this panel here is a control system to control the antenna. The antenna has to be handshaked against the radar. So the antenna has to tell the radar when to fire, because you can't be moving the antenna or you'll miss the beam coming back again. And so this points the antenna at a spacecraft using the public catalog position. which is probably good to about 5 kilometers, something like that. And then it tells, this is the radar acquisition computer, it tells this computer to fire, and this generates the pulses and records the recording, and it sends it to the basement, this is a terminal connected to that, to a supercomputer cluster comprising about 1,000 Xeon cores. And it crunches the data in about 20 seconds and then delivers back the results, and then that data goes out of a firewall off the secure internet and then is posted to the client in under 2 minutes. So we developed all of these in a software language called LabVIEW, which some of you may be familiar with. It's entirely iconographical. There are no lines of code. So it's all, if you look at it, it's like a giant Persian carpet. As opposed to a traditional script language. But it's very, very, very quick to develop things, and it's also fully multi-threaded. So in fact, in LabVIEW, if you don't specify the order of things, then it will do everything simultaneously. So if you want to have an order, you have to sequence. Otherwise, you won't. One of the keys to international business expansion is to have local representatives. It's fair to say that you would never get anywhere in Portugal unless you spoke Portuguese and you were familiar with the environment. You would think that everybody had the same legislative environments and so on, but you would be completely wrong. The US is even worse. It looks like Canada, but it is totally different legally. This is Phil Yude, so he's in Australia, he's in Carnarvon. So the first thing we wanted to do is get coverage in Australia because the Pacific Theatre is where the action is. That is where Russia and China are launching from. And so Phil ran the museum, the Carnarvon Space and Technology Museum on the west coast, right on the west coast of Australia. Because of its position, this antenna was built and a bunch of other antennas in the local regime to be able to see things. So this was the antenna that relayed the moon landings. And a museum was set up on site to commemorate that event, and all of the various moon astronauts have been there. But they ceased to use it in 1985. So one of my jobs is to surf the world on Google Earth looking for antennas bigger than 30 meters. And it turns out you can see them from space. And there's a handy little bar at the bottom, a measuring stick. So if you take your antenna over to the measuring stick, you can tell whether it's a 20-meter antenna or a 30-meter antenna fairly accurately. And so I found this antenna from space. I do my research to try and look. The Earth is huge. You're never going to find one just by randomly scanning a country, unless it's quite small. And starting at the airport. And so I found this antenna and I contacted Phil, and they're really keen to do something about it. So if you build a new antenna, as the Space Force is trying to do in Pembrokeshire in the UK, people come out and chain themselves to the trees to stop you from cutting them down. And they launch endless appeals against it because they don't want this infrastructure. They're quite happy with the environment that they have, and people are a little bit fearful of changing things. Maybe they won't like it. Once you build one of these things and you leave it there for 30 years, it's absolutely the opposite. The locals love this antenna. It is the thing that they use to navigate at sea. It's the only thing you can see. The planes bank around it when they come to land at the airport. I hadn't fully appreciated until I went to Australia how much they cared about this antenna. And it's like somebody gave me their baby. And so I do feel a great responsibility for it. So this was our first repurposing in another country, and we acquired this antenna about 2 years ago here. This is from last week, from one of the newspapers. They're showing them trenching the new power line into the antenna. We need more power than the antenna had originally provided. So again, this was built for the moon landings. These things are built extremely robustly, and we may need to replace all the electronics and most of the drives, but the mechanical and the infrastructure are pretty good. I alluded to Portugal. This is the ThothX Meridian team. So in each one of the countries, we've formed local teams whose responsibility it is in order to provide some kind of cohesive cohesion over the 6 ThothX companies now. I'm the CEO of each one of them, but I defer most of my authority to the local managing director, who's responsible for things like taxation and those kinds of things. Portugal, if you don't sign every single page in the document, it doesn't count. Your signature in Portugal doesn't count. Doesn't count. You can sign as much as you like. Unless you authenticate it with the authorized government application with your NIF, your National Information Number, it doesn't count. It's not a signed document. And these kinds of things you would just really not appreciate from outside. And so the ways of doing business in different countries is quite different. And again, everything's in Portuguese in Portugal, and obviously, so you need local representatives. So I was lucky enough to meet Francisco Wallerstein, and he was working in another space guy. He lives in the Azores, in Ponta Delgada, which is a small island in the middle of the Atlantic. If you want an international holiday, I highly recommend the Azores. It's 4 hours flight from Toronto, and yet it's in Europe. The streets are cobbled, it's European food, European coffee, and it's beautiful. And it never freezes. They have like azure blue lakes, and it is really quite something. So one of the cornerstones of the Azorean economy is space. And so they held a conference, which I went to attend. I was invited to speak. And I met Francisco. And in Ponta Delgada, there is another antenna. Again, the locals feel that the telecom provider had been neglecting it, and they wanted something done about it. Francisco was particularly keen to lead this. And so he developed a team of people who support this. And in each one of the developments that we do, we try to put together a small but effective team that can provide the support. And that also helps with things like the licensure, because as I alluded to, the Portuguese want sole authority over the Portuguese data. They don't want Canadians to have a kill switch, shall we say. And Europe feels the same, and the UK feels the same. The UK does not want a North American kill switch on any of their systems. And so this is leading to the rise of these local solutions. So it turned out we didn't really quite understand it because we started with this essentially a franchise model before, but it's working out very well. And then the local companies are also responsible for export control. So this is a control technology. It's ranging something more than 300 kilometers in range, and that immediately puts it on the control technology list. And so export permits and export licenses are required, and local companies are the way forwards. And the governments much prefer that. They don't want to deal with an international company. They want to deal with a local company who abides local rules and can be held locally responsible. So in addition, we do quite a bit of different R&D activities. The company draws quite a lot of R&D support through things like programs like Shred. If you run a small company, it's possible to get significant tax benefits if some of your work is in the R&D sector or the development of programs. So this is something that we utilize to support our R&D effort. So we've been developing ISAR imaging. I think I'll show you a little bit of that on the next slide. And we've been developing a LEO solution to start mapping all of the objects in geostation, in LEO low Earth orbit orbits. So this was a bit of a surprise. We didn't expect this. we started attempting to do inverse synthetic aperture radar. So radar gives you like a one-dimensional view of the object. You hit it and you get a return, and then maybe if it's got some structure further behind, you'll get some return off that. And so you'll get like a linear view through it. But mission controllers and commanders like videos and images. It's just easier, viscerally easier to make decisions if somebody shows you a picture. And so we decided to try applying inverse synthetic aperture radar to this. So normally the technique works because the object is moving. And so this is regularly used on ships at sea or by satellites that move over. Either you have to move or the object has to move. And so if the ship is pitching up and down, the radar will interfere with it in different ways. And then through a process called inverse synthetic aperture imaging using inverse Fourier transforms, you can build an image which provides data on the cross-section. And so it's a bit like if I have two reflecting phases here and my radiation is coming, I use 6 centimeter radiation. If I move each one of them 3 centimeters, now they'll destructively interfere with each other. And if I go back to 6 centimeters, then they're coherent again and I'll get a big reflection. You can take that and turn, using mathematics, and turn it to provide another information dimension in an image. So this is a spacecraft that we imaged. This is Viasat-1. This is in the clean room, deploying its antennas. This is its on-orbit configuration, artist's impression. And then this is an inverse synthetic aperture radar image that we made of this spacecraft at 40,000 kilometers range. And so you can see that we can begin to start picking out the antenna nests on this. And so that's very useful to determine whether it's the same spacecraft as before, what the purpose of the spacecraft is, whether there's any deployment issues on the spacecraft. And so we didn't actually expect to be able to build images because we required this motion. And so what we did, and we worked with MDA to try and prove a theory on this, is that we believe what happens is that the spacecraft control system slowly hunts backwards and forwards. And the spacecraft is about maybe 50 meters across. On orbit. And so that's big enough to produce centimeter scale deflections of the object that you're looking at. And so if we take a series of 60 radar images and we stack them, and then we do an inverse Fourier transform on them, then we can get this additional image direction out of it. And so this is something which is a work in progress. There are various ways to enhance the resolution by increasing the sampling rates and other techniques, and something that we're working with MDA because they deploy whole constellations of spacecraft deploying different but similar techniques. So currently we're deployed here. Next we're going to be deployed in Carnarvon. I just showed you that we're talking to BT about reutilizing their Earth stations, and then we've acquired an antenna in the Azores and another one in Lisbon. Expect to be operational in Lisbon. So fingers crossed by the end of 26 we should have global coverage on this problem. So that will allow us to see all the operational spacecraft in orbit. The dead ones you can see by observation occasionally. Once you finish with the spacecraft in GEO, you're not meant to leave it floating about because it might hit somebody else. You're meant to actually boost its orbit a bit higher. And so then it starts to rotate because it's not got exactly the same rotation rate as the Earth. And so they come and go every 2 or 3 weeks. And so most of the older spacecraft, anything with a number under 20,000 is probably dead by now because it was probably, that's like 70s. And so normally the later the number, the more recent the spacecraft, unless it wasn't catalogued previously. So it's not a surefire thing, but if it's a 60,000 object, chances are it's a brand new spacecraft. And if it's like if it has 4 digits, then it was one of the first things we ever launched on planet Earth. And it may or not be there by now. So this is going to allow us, this is the visibility curves, this is going to give us a global coverage over everything except a small section in the Pacific. So this is another way of visualizing it. This is a diagram by Hughes. Each one of the dots represents a $1 billion spacecraft in GEO. So you can see some orbits have a whole load of them. In Canada, our communication services are run by Telesat, who operate 3 spacecraft, Anik F1, Anik G1, and Anik F1R in a tight constellation about 10 kilometers apart in GEO. And the reason is that then they can load share. Your antenna sees all of them. If one of them goes down, we can move services from one of them to the other one of them and then not interrupt the service. If you can imagine for something like satellite TV, that's absolutely critical. Because if my satellite TV goes down, then 1 million people call the service provider and ask when their TV is coming back. And if I don't get it back to you tomorrow, by tomorrow, then 1 million people call other service providers and see whether they can get a service from them or not. And so rapidly the public loses faith in your service if it goes down for more than hours. And so in order to counter this, the operators hot swap their spacecraft, and they have 3 in a tight constellation. So if there's an anomaly with one of them, they can transfer the services over, and they don't find themselves waking up the next morning without any customers. And so, yeah, that gives you a kind of a visual image. And so it's like a ribbon around Earth, around the equator. They don't strictly have to be on the equator, but they're normally fairly close to the equator. Oh, this is one of my investment slides to say it's a growing business. Everybody likes upward trending and catchwords like TAM and KAGR. But the general impression is that space is really, getting utilized for our benefit now, and we've got to start doing things to make sure that it's sustainable in our usage. The first thing starts with monitoring. There are various strategies to start cleaning up space, but I would argue that before you're going to clean it up, you need to know where all the objects are extremely precisely, because if you're going to catch them or something, you need meter scale accuracy in order to be able to start intercepting some of these objects. This just shows the expansion of the business. Ultimately, we think that the insurance companies are going to be one of the primary markets here for if you can identify people's risk, then you can save money as an insurance company. And clearly, as I alluded to, different operators have different capabilities and performance benefits, and not everybody tells the truth. Particularly in Eastern countries, there is you don't want to admit liability to a thing. And so if you lose control of your spacecraft, it's kind of embarrassing. And so you might deny it for a while, even if other people know. And so this happened recently in Malaysia, where they lost control of a brand new Boeing spacecraft. And they denied it for 3 days. But the US military knew. And the civilian operators also detected that the spacecraft had spun up and was spinning very rapidly and knew as well. So eventually you have to come clean. And that is actually one of the biggest growth businesses for us. So the US military know all sorts of things. But if they are developed using classified hardware, then it's going to take about 3 weeks for me to tell you what it is, because it's going to take 3 weeks for the US military to declassify it. And so that's going to make a big impediment to using that data. So actually one of our markets is to provide unclassified data to the US military that they can show to other people without disclosing military secrets. And so they're very big on this. They, because they have these problems, like the Malaysians losing one of their spacecraft and saying there was nothing wrong, nothing to see, nothing. But we know there is, but there's nothing. So you can see why that would have it's a big defense contractor for the US, and they have a vested interest in whether that spacecraft is malfunctioning or not. They want to know. So that's a big rise where one nation might want to show data to another nation, but they don't want to show their classified data because that might reveal ways and methods as to how that data was generated. And this is just a quick concept of operations. So we basically get a list of numbers, which are NORAD IDs for spacecraft. And then it comes to us, and then we target the antenna at the spacecraft and we point the radar. And then we fire the radar and we track the object over about a series of 6 measurements. I can't just observe it once because this is the most accurate measurement there is, and so there's nothing to compare it against. The only way that we know that it's not just a false hit or an RFI is if we hit it multiple times and get the same answer each time independently. And so typically we fire 4 to 6 shots. And then we take those, and then if they're all in a straight line and there's just a slow velocity change, then you know that all the measurements are good. And then we basically post it online to a repository. So it would have taken me about 2 hours to draw this diagram. And instead it took me 30 seconds to dictate this into ChatGPT-5 as to what I wanted in a diagram. It took ChatGPT-5 about 2 minutes to generate this pictogram, and I would never have done it as well as this. I would never have got these little tiny pictograms. So even if I'd spent 2 hours or more on that, it wouldn't have been as good. So these tools definitely have time-saving utility, I believe. Will they make everybody redundant? I highly doubt it. But are they a productivity saver? Yeah, they definitely are. Now, clearly some jobs are more at risk than other jobs, but somebody has to harness the creativity of the AI. There are definitely limits to the performance of AI. AI is fantastic at summary. If I take a big document and I give it to it and I tell it to write a small document, it writes something better than I could. It's terrible at expansion. If I give it a small document and I tell it to write a document with twice as many words, it's total gibberish. It just comes out with just total nonsense out of the end. And obviously it will get better and it'll improve in the different ways, but there are definitely some systematic limitations to it. Just as another aside, it's not very deterministic at the moment. AI makes mistakes. In this slide, I had to tell it to, actually this has got the wrong one. You notice it misspelled targeting. Now, how can a computer misspell a word? And so I think that this might be a real-world identification of the row hammer problem that GPUs have. And so GPUs are known to have a vulnerability where if I hammer one row in the memory, in the physical memory, I can flip bits in the other one. So there's something like that's going on here because it's transposed to, like any word processor from the 1980s would have been able to spell the word and flag it it's wrong. But here we are using the latest AI business edition. It's misspelling words in the middle of captions. So it's a fantastic technology. It's clearly got growth, and it produces beautiful diagrams, even if they have the odd spelling mistake in them. So lastly, this is the display terminal that the data comes out on. And so I went for a tour of North Bay where they control the flight control. So we have a totally integrated flight safety system with the Americans. I have absolutely no fear that the United States are going to invade us because of the military people who come and see me, 10% of them are US citizens wearing Canadian uniforms, and 10% of them are US citizens wearing US uniforms. Those are observers. The other ones are embedded. The top general, General Whale, who actually lives locally, was the top space general in the US Space Force for a while. Our militaries are totally integrated, and so any kind of invasion of Canada would involve them telling to kill each other, their friends. And so I really don't think that's going to happen. So we have this, this totally integrated military solution. So one of the things at North Bay when you go is they have giant monitors for plane management. So these are the people who determine whether we're going to shoot down a civilian airliner. They have one desk and it has a big monitor and there are boxes, and every single plane over the sky of Canada is in one of the boxes. If the plane goes outside the box, the desk has 2 minutes to contact that plane. They have absolutely every flight control tower on speed dial. They can be patched into any cockpit. They have 2 minutes to speak to the pilot and ask them why they're not flying along their flight plane. If they don't get a reply, it goes to the next desk. Those guys have another 2 minutes to remediate the situation. If that doesn't happen, it goes to the command desk. The command desk makes the determination as to whether this is a threat to Canada, and if it is, they can co-opt any F-16 in the air, in flight, US or Canadian, to go intercept those spacecraft and those aircraft. And they will show up on the wingtip of the plane and use signals, if they have to explain to the pilot that they better land. If that doesn't work, there is a big shiny red phone that they call the Americans on, and then there's a $15 phone from Radio Shack that they call the Prime Minister on. So they call the Prime Minister on the phone, and he is the only person, or she is the only person who's authorized to shoot down a plane over Canada. And so if it's a risk, the Prime Minister has to authorize it, yes or no. And that's how we do plane safety management. It's very kind of similar to the analog as to what I'm doing, and so they have these big displays, so I decided I'd have big displays which were nicer than their big displays. And so we developed all these Ultra 4K interfaces. So on this one, this is the analysis pane. We're showing 3 spacecraft, ANAC G1, F1R, and F1, all in the same observation. And so down here we're showing the automatic targeting, and it's identified the 3 spacecraft here, so that's going to go out in the metadata. This is goes on for 8-hour sessions, so traffic lights are easy for the operator. If it's all green, everything was good. If it's not green, then somebody needs to do something about it. And then there are various different kinds of settings where we can do more advanced features and program it. Because it's software defined, you can change almost any parameter of the way that the measurement occurs. The trick is not to. The trick is for an operational environment, you want to do the same things over and over and over and over again exactly. But for research purposes, it's quite handy to have them. Because this is a very innovative new technology, there are quite a lot of switches that we don't use anymore. So they were put in to test various different functions, and then they just become obsolete. But they stay in the back of the code should we need to develop that. Everything that we fire always goes to a database that logs it. So I have every single raw binary record of every time I fired the radar. Disk space is cheap these days. You can have 30 terabyte drives and store 6 months of radar data on one, and before you move on to the next one. And then I have an SQL database that logs all of the radar results, so I can just quickly look up what happened, what it looked like before, and do a quick change analysis on it to determine whether it looks like it did before. So I think that's my last slide. Yes. And I'm sorry if you were looking for more information on the old dairy and what we're doing there, then you were disappointed by this presentation. But I'm happy to answer any questions about this or that. Thank you.
So, questions, please. Paul?
Did you want to use the mic or just?
Oh, yeah, good idea.
Just curious about how you identify the object. You know the distance to it, you know its location in circular. Are you identifying it by inference from where it is?
Yes.
Okay.
So NORAD published what's called a 2-line element set for each spacecraft. It contains about 10 parameters that allow you to compute the location in real time. It's published every 3 hours. It's probably good for a day or so before the data gets too stale. It's a multi-polynomial parameter fit to whatever they think the underlying orbital model looks like, with a little bit of guesswork in it. It's accurate to about 5 kilometers. And so once I use a Bayesian inference algorithm where we ask Bayesian questions like what is the probability that this object is based on its angle, its and range, and we do it to all 50,000 objects so as we don't cheat. One of the things about it is if you feed in the same information as you're looking for, as I discovered in other physics studies, you can find the answer that you were looking for because you put it in at the beginning. So you have to be very, very careful with a priori estimates because they can come to influence your answer. So we don't tell the analysis filter what the spacecraft is. It doesn't know what we think we're looking at.
Thank you.
Okay.
Yeah, it was a fascinating presentation. Really enjoyed it. Thank you very much. And I could listen to another 3 hours if you had more. But anyways, one question: do you feel vulnerable even when you get the satellite or the systems in Australia and in the Azores and whatnot? It's still only 4 in the whole world. So do you feel like there's a vulnerability that one of your dishes could be taken out, even just by forest fire, for example?
Yes.
Okay. And
So the plan is for 10.
okay.
So the global domination plan.
Right.
Is for 10. Also, most of these antennas are on what's called safety critical infrastructure sites. And so they are quite hardened. So like the BT site, for instance, has 12-foot razor wire fences around it and 24-hour surveillance. So these are not, the Algonquin one's a bit anomalous. But we have our own security. We have the bears. And you have to find us.
Okay, thank you.
Yeah.
And another question, so the system is supposed to keep track of all of those, however many thousand satellites in geostationary orbit, but it seems like when you want to look at one, you have to point the antenna exactly
Yes.
at it. So in a given day, how many can you actually look at? Because it must take some time to...
Right.
to
So our throughput is about 12 objects an hour.
okay.
And so currently the ND has a list of 160 objects they're interested in, and they're thinning it to me to 30 objects that they're really interested in. And so we can provide more of the coverage. We could look at every object in the sky about every 8 hours currently with one antenna. So that if we want the kind of cadence that NASA publishes a high rate revisit list where they would like data on 3,000 objects every hour. And so that's almost aspirational in terms of the kinds of volumes of data provided. So my estimate is you need 100 antennas globally to provide an hourly update on every single object, which would be kind of the gold standard
Right.
of latency and cadence.
Okay, thank you. And final question, how many people is ThothX?
We're about 10, 15 globally, somewhere between 10 and 15. It fluctuates a bit depending on how you count a person. So there's typically a team of about 5 in each one of the countries.
Right, okay. Yeah, thank you very much.
Further questions?
So since there are thousands of satellites in space, I'd imagine there's a lot of debris floating around. And does that cause any, I imagine that must cause problems. How common is it for satellites to collide with other satellites or broken satellites? And are there any projects in place to remove the debris?
So small collisions are very common. Big collisions are less common. So some of the, like Iridium, one of the Iridium spacecraft hit a defunct Russian spacecraft a few years back and caused a really noticeable rise in the flux density of objects in that orbit. If you think about it from the operator's perspective, it's a terrible thing to do to your business because you're destroying the one asset the orbital asset that you're using in order to do it. So you definitely, everyone has a vested interest to not do that. Various people have various plans about debris mitigation. It mostly revolves around gossamer nets that capture high velocity particles and trap them and then deorbit them by increasing their drag, or grappling where they do the same thing. You basically grab a hold of the object and then try and deorbit it. I think for large objects, that's kind of in the technology demonstration realm, and it can be done. For the small objects, it's going to be much harder. A fleck of paint about less than 100 milligrams broke one of the windows on the shuttle. The Chinese are currently abandoning one of their return vehicles because it was hit by debris. And one of the major shuttle accidents was caused by debris falling off the spacecraft and striking the wing during launch. So these things are quite common. If you are in low Earth orbit, you should be expected to kind of get peppered by small debris. So there's a bit of a game of chance over it. The orbital velocities in the anti-orbit, the objects are coming at you at 18 kilometers a second. And so that's far faster than a bullet. And so the kinetic collision impact is very, very large. So you're not going to be able to, like a gram of an object is good done. From my perspective, the technological challenge is tracking those objects. We have an aspiration to track everything bigger than 10 centimeters. But again, if you're hit by a 10 centimeter object in space, that's like being hit by a train. First the knowledge has to come. Maybe we can start cleaning it up, but it's much better not to pollute than to try and clean it up after the fact.
I have one. In fact, I have two. If every one of these satellites is traveling in a relatively almost the same orbit, how do they get such relative speed so that they'll cause damage?
Well, they might not cause damage to each other, but they might cause interference if they get too close. But they could also you could also have objects in the anti-orbit. And if you blow something up, then you're going to have all sorts of different kinds of
Well, so they're not always going the same way around.
Right, and then there are objects in GTO. So to get to geostationary, you launch into low Earth orbit, and then you progressively elongate one of the axes of the rotation till you get one of the primary axis out to geo, and then you circularize the orbit. And so during that process, rocket bodies get left behind in GTO, and so you've got it's like a giant, all sorts of whirling objects.
Great. One last question. I know that you're sometimes seen in town. Do you have people running the telescope, or do you run it automatically from Deep River, or do you have to be there in order to run it?
So very topical. Currently somebody has to be on site to run the antenna, but the objective is to be able to run it remotely from Deep River. It's not always easy to get into the middle of the park at all times. But there are a number of issues that prevent us from remote running. So if you're going to remote run something, you need to have two computer systems, totally independent of each other. And so we just put in what we call the watchdog system. So we now have an independent computer system whose job it is to make sure the antenna is only being operated within its envelope of operations. So that is, the rates aren't too high, and it doesn't stray out of the angle space that it's allowed to be in. And if it does, it presses the emergency stop button.
So it won't destroy itself like
So it
it
won't
did
destroy
last
itself.
night?
Right. Yeah. So that was a big issue for us, what happened to the antenna and why it was so damaged. We wondered about that for a long time. When we took the gearbox together to pieces, this 35-ton gearbox had massive damage. There were pieces of stainless steel the size of my fist rounded into balls out of it. So it had been damaged for a very long time. Through the huge torque of the antenna, it's basically smoothed out all of these bearing chunks. So we wondered why that damage had occurred. I thought maybe the hurricane in 1999 had caused it, but if you do the calculations, the wind load is not enough to do it in. And then a postdoc from U of T came, and he said he was up in the antenna, and someone was operating the antenna and giving a tour at the same time, and they forgot about it, and they ran it into the end stops at full speed and elevation, and he was in the antenna, and he said it rocked backwards and forwards on top of the tower. And so if you do the minimum calculation that you could feel a rocking with about 0.1 degree, then it would have overloaded the bearings. The force that it fell against would have overloaded the bearings by a factor of 10. And so that would have destroyed the bearings. So
that will destroy it.
that's probably why it was. And so then we had a diagnostic, because we spent an awful long time trying to fix it. And then we were kind of wondering what we could do to stop that from happening again.
Okay, if there are no more questions, could everyone please just...